We're in chapter 3 and talk about Lewis structures and bonding. And last time we got into really sort of drawing Lewis structures. For really covalent molecules. And when we draw really Lewis structures for covalent molecules, there's a lot of steps that you should follow to draw the structure. Again, really one of the most important things, obviously, when you're doing it is the number of valence electrons in the actual molecule. And again, we really want the total number of valence electrons. We want them to think of them as being necessary to distribute through the entire molecule, not necessarily maybe belonging to one atom or another. That way you don't end up with sort of piecework and trying to make the wrong number of bonds. Also, the logical sort of arrangement there of the atoms. And remember that it is usually the least electronegative atom that should be in the center. Bless you. In a lot of cases, everything else is attached directly to it. Sometimes you can have multiple central atoms, as we saw, I think, in nitric acid that we drew. But it really does sort of work the same way, but that least electronegative atom there should be in the center. That means, again, fluorine should never really be in the center because it's the most electronegative atom you can have. Also, hydrogen should not be in the center, again, because it would have definitely more than 2 electrons, which it should not have either. Once you have the logical arrangement and really the number of valence electrons that your picture should have, you really just want to do one single bond, really from the center atom to all the outside atoms. If you happen to have multiple central atoms, then also include that one as well. Once you do that, you will have used up a certain number of your electrons. Again, 2 for each line, obviously, that you draw. The remainder of those electrons do go on the outside atoms in pairs of electrons. So those are going to be dots until really all the outside atoms meet the octet rule and pretty much have 8 around it. Obviously, the exception to that would still be hydrogen. That should not have any dots around it or anything like that. If you fill up all the outside atoms with electrons and they're all good in terms of sort of the octet rule, any leftover electrons at that point should go to the center atom and also should be put on as pairs of electrons or dots, basically. At that point, you really should be out of electrons. The last thing that you want to do is, after obviously outside atoms, dots of electrons, then center. The last thing you want to check, obviously, is that the octet rule is met. If it's not met, is really at that point, it's a good idea to try to fix it. And as we talked about, you usually don't want to double bond or triple bond right out of the box, but maybe save it to sort of fix a situation where somebody maybe does not meet the octet rule. In that case, you would really want to start with double bond first, try to exhaust all the possible double bonds to fix it. If that should not work, then you may have to go to a triple bond to do it. Remember that when we do make something, if we just still like an oxygen here, right? If we want to make a double bond, we do need to bring those electrons in to make it. We can't just add electrons, otherwise we'll have too many electrons. We can't just add a double bond, or again, we'll have too many electrons. So we do bring those electrons in to do so. If you need to make a triple bond, same thing happens. You just bring another pair of electrons in to make that triple bond. At that point, you really should have a fairly good structure that is drawn. The other thing that we talked about, I think, towards the end last time was the idea of formal charge. And formal charge is sort of the charge that each of these atoms basically take upon in this sort of covalent bonding situation through sharing of electrons. And some things will take on some different sort of formal charges depending on sort of who they're sharing with. To calculate the formal charge, you take the number of valence electrons in the atom by itself minus the number of non-bonding electrons. And these are total electrons, minus 1/2 the number of bonding electrons. And that will give you the formal charge on each of the elements you could really do it for in a Lewis structure sort of picture. The sort of benefit of formal charge, or a lot of times what people will sometimes use formal charge for more specifically, is it can help you maybe pick between two possible structures that you might want to draw. And I think we did a couple of those towards the end of last time as well. And it can help you decide between two structures of which one might be a better structure than another based on formal charge. Overall, the general rules when trying to decide that is pretty much if you could kind of minimize the formal charge to zeros, that is sort of the best deal, or get everybody as many down to zero and the rest down to a sort of small number is really probably the best sort of situation. If you have a distribution of formal charge which is similar between two different molecules, you would want the more negative formal charge on the more electronegative atom. That's also a pretty good thing. And also really large sort of formal charges is probably not going to be the best structure that you'd get. So again, a sort of application of formal charge is that you can use it to help yourself sort of decide between different sort of structures. Any questions on that stuff we talked about last time there? All right, so I think that's sort of where we left off. So let's talk about a few other things here. We did talk a little bit about resonance structures as we were going through drawing Lewis structures, but let's talk a little bit about bond length first, and you don't have to memorize these numbers or anything like that. But these are the typical bond lengths, which is really the distance between the different nuclei and between two bonded atoms. And when we look at these sort of numbers, for example, we have the carbon-carbon single bond, double bond, and triple bond. The distance for the single bond, 154, 133, and 120. If we look carbon-nitrogen, single, double, and triple bond, it goes from 143 to 138 and 116. So the trend that we generally see is as we continue to sort of put bonds on between two atoms, pretty much everybody gets closer together. So if you think about how we draw the Lewis structure, that we're bringing electrons into the center, that's going to bring a bigger negative charge between the two, right? It's going to make those nucleuses come in closer to each other. And if we bring another set of electrons in to do a triple bond, it's going to bring everybody again in closer to one another. So basically, as we continue to put bonds on, the distance between those atoms in that bond get closer to one another. So the longer sort of trend there is with our single bond to our double bond to our triple bond. And that also relates to sort of strength. Typically speaking, a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. They're not like 3 times as strong as a triple bond to a single bond, but that is a general trend that you see. And as we just talked about and just saw on that chart, again, in terms of length, it's sort of opposite, longer for single and much shorter there for triple. So you can kind of think of it like a brand new pencil, right? If you have a brand new pencil and it's pretty simple, you can snap it, not too much problem. You take a couple of chemistry tests, you're left with like a nubbin and a little eraser, right? If you try to break that, it's super, super hard, right? Because everything's like compact near each other. So it's much harder to break. So it's sort of the same idea of what we see there with our strength of our bonds. So obviously, as we were talking about earlier, we talked about electronegativity. And again, that is our attractive forces that's going to bring our electrons towards one another. And we talked about the different types of bonds and the electronegativity difference that we could use. And again, depending on whether it's a non-polar bond, I think was another thing that we talked about last time. Again, a non-polar bonds where we have a difference in electronegativity anywhere from 0 to 0.4 is considered sort of equal sharing of electrons. And as we talked about, there is a degree of that equal sharing. Again, a reminder that if you technically have a electronegativity difference of 0, it is considered sometimes a pure covalent bond, which is still a nonpolar bond. It's kind of like your perfect equal sharing of electrons between it. 2.4, which is still considered equal sharing of electrons, but obviously there's a slight unequalness that happens in that sort of range. And again, a nonpolar covalent bond is the equal sharing of electrons, and the importance of that is it really creates sort of like a neutral bond, if you want to think about it that way. There's really no side of that bond that's more negative or more positive. And obviously above that 0.5 to less than 2, you do get some unequal sharing of electrons, which is our polar bonds. And again, that does create that sort of positive side of the bond and negative side to a bond as well. And again, typically metal and non-metal will get you a ionic bond. And I think these are some of the examples, are similar examples to what we did before. Now, when we talk about bond polarity, as we touched upon, I think last time as well, that is really where you use that difference in electronegativity values. And it will tell you specifically, again, between those two atoms, if that bond is going to be polar or non-polar. And again, you really don't need it, as we talked about, for ionic bonds, because it should be a metal and a non-metal. This is the one place, as we talked about, that bond polarity, and again, sort of molecular polarity, which is the polarity of the entire molecule as a whole, really does sort of cross over. So this is really the one place where you can look at bond polarity and molecular polarity and will be the same. And that is when we pretty much have a diatomic molecule, as we talked about. And we'll talk more about molecular polarity in the next chapter. But in these sort of simple molecules, which are really just two atoms together, you really can basically, this is the same thing, the bond polarity and the molecular polarity. And if a molecule as a whole is polar, it will have what is sometimes referred to as a dipole moment. So a dipole moment is only found really in polar molecules. So these are found in polar molecules. And if you remember, in the bond dipole, we draw that arrow that looks like this, where again, it points to the more negative side. And again, this side being more positive, which kind of makes like a plus sign in the back. That is also the same arrow that is used for a dipole moment in a molecule. So you could have individual bond dipoles, which are drawn with these arrows, and those little guys, arrows, basically will represent the individual bond polarity that's there. And you could have another arrow that's drawn that looks the same as those arrows, and that will represent the entire molecule, you know, which one is polar, or which side of it is more negative, which side is more positive. So we'll touch more upon it in the next chapter, but just to give that illustration, we looked at something like water, for example. Water has some polar bonds, so it has some bond dipoles between the oxygen and the hydrogen, as they do have differences in their electronegativity values. And you can, for something like water, draw an overall bond dipole arrow that represents a bond dipole moment heading in this direction, which tells us, as we will talk about, that the oxygen is actually more negative overall in that molecule of water, and the hydrogen side is actually more positive in a water molecule. So sometimes confusing for people is those arrows is kind of used for both of those things, bond dipole individually just between those two atoms. Is it a polar bond or not? And that same arrow is used for dipole moment, overall molecular polarity. So getting back to sort of the diatomic molecules, they will be really the same as the bond dipoles, and I think we might have talked about, but again, something like F2, that is a non-polar bond. And because that is the only bond, once again, that is going to be a non-polar molecule. And something like HF, again, that we saw, does have a polar bond heading in that direction. And once again, because this is the only bond, it will also be a polar molecule. So in the case of something like HF here, that bond dipole arrow is also the dipole moment that we would see in that particular molecule. And that means that really this molecule, the fluorine side is more negative than the hydrogen side in this particular case, so they do overlap. So that's the one place in terms of polarity where bond polarity and molecular polarity are pretty much going to be the same. As we'll see in the next chapter, when you have multiple atoms involved, you do have to look at several things to determine whether or not the molecule is polar or non-polar. And as we will see in the next chapter, you can have polar bonds, but the molecule actually be non-polar. So there is a lot of things differently that you have to look at when you have multiple atoms involved. Any questions on that there? And again, here you can see obviously non-polar bond here. Overall dipole moment is 0. And these all are polar bonds. And it has dipole moments. And in an ionic bond, you can see the dipole moment is really big because the electrons have completely transferred. So clearly in that sort of scene, there's a full positive charge and full negative charge that's occurring rather than those partially positive or partially negative charge. And as you can see, there's a very big difference. If you actually calculate a dipole moment, which we will not be calculating, but if you actually calculated it, there's a very big difference in that because of that full transfer of electrons that occurs. All right. So let's talk a little bit then about energy, and be the one place probably where we will talk about energy and bond energy. And the idea of bond energy is, as we saw in that sort of chart earlier, there's a certain amount of energy required to break a bond. And there's also a certain amount of energy required really to make a bond. And those processes are different in terms of energy and what happens when we make and break bonds. So when we break bonds, it is a endothermic process. So you got to bond together. You actually have to put energy in, and as they gain that energy, they wiggle away from each other, exactly like that. And basically the bond will break as they have enough energy to do so. When we actually make a bond, they have a lot of energy, so they actually have to release that energy to allow them to kind of slow down so that they can kind of come together to make the bond. So making bonds is actually an exothermic process, and breaking bonds is an endothermic process. A reminder that when we talk about energy and sort of endothermic, it's usually a positive value. Exothermic there, as we talked about when we talked about electrons transferring and stuff, is a negative value. So it has to be released in this case. So really, in a chemical reaction, the only thing that happens is as we go from the reactant side, which is our starting side, to our product side, which is where we end, basically all these bonds over here get broken and all these bonds over here get made. So really, to calculate the bond energy, which is sometimes referred to as the delta H, which is the enthalpy, you basically take all your products and all the energy of your reactants, and you basically take the difference between them, add them together. So the energy required to break all your bonds and the energy required to make all your bonds. And you basically want to keep track of how many bonds you're making and breaking. Now, this may require you, if you're not sure what something looks like or what bonds are present, to quickly maybe sketch the Lewis structure so you don't miss a bond. It's very common sometimes when people maybe don't do that and they just take the equation with just the formulas. A lot of times people miss bonds. Sometimes when there's like organic guys where carbons are attached to carbons, that inner bond, sometimes people miss making and sort of breaking those. They just think about sort of the outside bonds. So sometimes it's helpful to draw the Lewis structures so you can actually visually see which bonds you're making, which ones you're breaking. Also important to draw good Lewis structures because, again, some bonds may not be single bonds, right? They may be double bonds or triple bonds, which will require different energy input or output, right, depending on what you're doing with it. So if you're not sure what it looks like, a quick Lewis structure sketch is usually a pretty good idea to do. So this is a table, for example. You have a similar one in your book. But as you can see here, these are the values again, which are sometimes referred to as bond enthalpy. And You can see it is different, obviously, values for single bonds, double bonds, and triple bonds. So again, that's why it's important to know sort of what bonds you are dealing with. So if we were to look at one, for example, this guy here, here it is. So we have CH4 and Cl, and that's pretty, I think I lost some things along the way there. So CH4, Cl2, we'll just do it here. So we have CH4. Oh, I can see the actual numbers plus Cl2 going to make our guy here. And this should be HCl there. All right. So if we have this guy, and again, just kind of quickly draw the Lewis structures, the non-bonding electrons are obviously not included in here because really in this case, we're just interested in the bonds that are happening. So if we think about sort of our reactant side here, we need to break all these bonds. Bless you. So all these bonds on the reactant side does need to be broken. So if we take a look over here at the CH4, there's a carbon hydrogen single bond, and there's 4 of those that need to be broken. So if we just make like a little list over here, broken, we have our carbon hydrogen single bond, and there are 4 of them. So we would find that right there, actually. So that is 414 kilojoules times 4, because we are going to break 4 of them. The other bond that needs to be broken on that side is the chlorine-chlorine single bond. And we would want to find that on our list here. And it's down here, it looks like, right there. And we only have 1 of those, so that's going to be 243 kilojoules times 1. And that should take care of basically all the breaking. So if we do that, grab a calculator, which would probably be helpful. So in terms of our breaking side here, we got 4 times 414 plus 243. It's going to be 1,899 kilojoules, right? Now, on the other side, we're going to make some bonds. And when we look on the other side, we have 1, 2, and 3 of the carbon hydrogen single bonds. So we're going to do 414 times 3. We also made a new bond here, which is our carbon chlorine bond. And that's right there on the bottom, which is 339 times 1. And lastly, here we also made a hydrogen chlorine bond, which looks like it's right there. Looks like 431 there, 431 kilojoules times 1. And that's all of our making. So we'll do 3 times 414 plus 339 plus 431. Looks like a 20. Well, looks like here, kilojoules. Now, as we talked about earlier, our breaking part, right, when we go to break bonds, that is a endothermic process, which means really all these values here are positive, right? When we go to make bonds, it's a exothermic process, which means really all these values here are negative. Which means that should be actually negative. Now, to find the delta H for this reaction, we're just going to add up those numbers. So we're going to take all the ones to break, which is positive 1899 kilojoules. We're going to add it to our negative because we kind of put the negative in there. So we're good, 2012 kilojoules. And that gives us overall for this reaction based on bond enthalpy, 1899 plus a negative 2012. Going to give us a negative 113 kilojoules in this case. Overall, this reaction based on bond energy, is it endothermic or exothermic? It is exothermic here as we have a negative value for our delta H. So this is going to be exothermic. So overall, the process of making and breaking these bonds, this reaction will release a certain amount of energy left over as that process occurs. Again, a reminder, delta H, which is basically about energy, positive, endothermic, delta H, that is negative, is exothermic there. Any questions on that one there? All right, so why don't you try one here? That's one we just did, I think. You also can, in that case of the last one, since we broke 4 carbon hydrogen bonds and we made 3 carbon hydrogen bonds, the net difference there is just 1 carbon hydrogen bond. So you could kind of take them out if you want, because they cancel each other out, or you could leave them. Why don't we just do this one? Why don't you do N2 plus H2 makes some NH3, and we need 2 of those, and let's do 3. Okay, let's take a look. So if you kind of sketch these, it looks something like this, which you might want to do. You may even want to, because there is a coefficient, sketch all 3 of them so you don't miss any of the bonds. And then on the other side, we have NH3, which basically kind of looks like this. And again, there are 2 of them, which means we have another one that looks like this. So once again, everything over here, we're going to break. Everything over here, we're going to make. And again, obviously, as you can see, you do need to take the coefficient into account. And again, sometimes just visually drawing them all can be really helpful. So looking here in terms of what we're going to break, we obviously have one of these nitrogen triple bonds. So we got that guy there, and that is going to be 946 kilojoules needed to do that. We also are going to break 1, 2, and 3 of those, again, because of the coefficient, and they're all hydrogen single bonds. Times 3, basically. So 3 times 4, 36 kilojoules. And I believe that is all the breaking we're going to be doing there. So that's going to be 946 plus 3 times 4, 36. Going to give us 2254. And again, breaking going to be endothermic, which means all these values are positive. Now, in terms of our making side here, we are going to make 1, 2, 3, 4, 5, and 6 of the nitrogen hydrogen bonds. So nitrogen hydrogen times 6, and that is somewhere where I'm at there. Nitrogen hydrogen 389, it looks like. So 6 times 389. Gets us 2334, looks like. This is going to be negative, as making bonds going to be exothermic. So now our delta H here for this reaction would be our positive 2254 kilojoules for our breaking, plus our negative 2334 for our making, or you could obviously just subtract it if you like, which is basically what we are doing. 2254 minus 2334. And in this case here, try that again, put the right numbers in. 2254 minus 2334. Going to give us a negative 80 kilojoules in this case. Once again, this would be exothermic, as we did get a negative value here for delta H. Any questions on calculating the enthalpy based on bond energy? And again, sometimes referred to as bond enthalpy as well. Okay, so clearly the chart would be provided for you. Yes. Right. Here's another example, and again, it's pretty much what we just did there. But again, drawing these guys out can be very helpful, so you can hopefully see it's a double bond. And again, drawing something like peroxide out, a lot of people will miss that central bond between the 2 oxygens if they just kind of go from the H2O2 sort of the formula. So it's a very common thing that sometimes that center guy gets missed. And then that should be what we end up with here, I think. in terms of it. So overall, in that case, if you did the numbers, you'll end up with minus 136 kilojoules. And again, that is going to be exothermic as well. All right, we did talk about resonance structures earlier when we were drawing, but again, officially resonance structures do develop when really you do have more than one option as to where you can lay up that, say, double bond in a situation. And basically those double bond electrons are delocalized, which means at any given point, they kind of are moving around from sort of one atom to the next. So one Lewis structure doesn't adequately sort of describe what is going on. And really the sort of correct structure is probably somewhere between all those resonance structures. So an example, ozone, I think we might have drew as well. Those are the formal charges on the atoms that we think we calculated as well. Again, really could double bond to the left, double bond to the right. And again, those double bond electrons are really moving from one side to the next. I think we also drew carbonate along the way there. And that's carbonate with its formal charges in there. And really what we're seeing here is those double bond electrons, again, just really kind of delocalized, moving around. Again, the true structure is somewhere between all those guys. Benzene is actually an organic compound, and it's these are all carbons, by the way, all attached to each other, and actually has 3 double bonds. And obviously, if you don't put the carbons in, which you typically don't, it's drawn like that, or you could have the double bonds sort of happening on the other directions. And sometimes in non-true organic books, a lot of times people will just draw benzene with like a little circle in the middle to indicate that those double bond electrons, again, are sort of moving around from one side to the next. So if you go off to organic at some point, you will draw it, and most likely you will probably not use the circle version. You'll use one of those versions usually when you do it. Here's another example of, obviously, you could have several different resonance structures depending on sort of where you move the double bonds around. For us, you do not necessarily have to draw all the resonance structures unless the instructions tell you to do so. If you draw just one structure out of them, then that should be sufficient. Again, unless the instructions obviously tell you to do so. Lastly, in this chapter, we're going to talk about some exceptions to the octet rule. So 8 is really sort of beat into everybody's head. But there are several exceptions to the octet rule. And in this class, we do come across some of these exceptions a lot. The first type of exception to the octet rule is what is known as an incomplete octet. And an incomplete octet basically means it has less than 8 electrons around it. Beryllium hydride there has, as you can see there, only 4 electrons, and it's okay with that. Really, boron for the most part, aluminum as well, but most of the time boron is the major sort of contributor to less than 6. It's electron deficient, is happy with that sort of arrangement. It's okay. It has obviously only 6 electrons around it. So probably in terms of incomplete octet, that's probably the one that you would see probably the most, some type of boron containing guy. Technically speaking, that's a metal and non-metal happening, but beryllium and also aluminum can kind of do that as well, sort of being electron deficient. But borons in a covalent sort of circles, really the most common one that you will see. It also later on, if you take 200B, you'll learn about it, but it's also will be able to act as a Lewis acid, and because it's electron deficient. The next sort of exception to the octet rule that we may come across, and probably not too much out of the 3, is an odd number of electron molecules. So it is possible to end up with an odd number of electrons. And what that basically means is you'll end up with one unpaired electron. So you'll end up with something that's unpaired, as you can see here on the nitrogens. We got one unpaired electron that's happening. It happens a lot in atmospheric chemistry. Free radicals have, unpaired electrons, which is why they're very reactive, because, they really don't want to kind of be that way. So they sort of try to react to fix that situation. but a lot of chlorine up in the atmosphere kind of ends up that way. And it can't be very, very reactive because, you know, it does want to sort of complete that octet, so they react very much. Probably out of the 3 sort of exceptions to the octet rule, the last one is the one that we will come across the most in this class, and that is the expanded octet. And there are several things that can go above 8 electrons, and that's what's referred to as the expanded octet. You could get upwards of 10 to 12 electrons around a central atom. And that is, like I said, probably the one we'll see the most, followed very far away, probably by an incomplete octet. Probably very rarely we'll come across too much of the odd number of electrons. But the expanded octet happens when you look at the periodic table and you find your friend sulfur. And you go to the right, you go to the left a little bit, and you go down sort of in the non-metal-ish area. And those guys have the ability to go above 8 electrons and do the expanded octet. And that is because sulfur right there is on period number 3 on the periodic table. And period number 3 on the periodic table is a principal quantum number of 3. Yes. And that means that L could be 0, 1, or 2, right? Which means that's an s orbital, a p orbital. And on the 3rd energy level, that is where we first start to see the d orbitals appear. So although they may not be using the d orbitals, they got all those d orbitals to house all the extra electrons. And that's how they're able to do the expanded octet. Because right at that point, and again, since we're talking about covalent bonding, really talking about the non-metals in that area there, left, right, and down, are where you can go to the expanded octet. That means, by the way, if we go above sulfur on the periodic table, like NOF, that is period number 2, which means N is equal to 2, which means L could be 0 and 1, which is an S and a P and no D, which means those guys can never, ever go over 8 because they have nowhere to put the electrons. So those guys always has to obey the octet rule. Sulfur and kind of below, again, to the right there where the nonmetals are, have the ability to go above 8. And we definitely will see it a lot here. So an example of that is SF6. You may be asking, you know, how do you draw your Lewis structures? You really follow the same process that we did earlier. So sulfur, which is group 6, and there are 6 fluorines, which is 7 each there. And that's a lot of math for this early in the morning, but that's 6 times 7 plus 6. That's going to be like a 48. I'll go with that, maybe, if I did that right, hopefully. So that's going to be 48, I hope. So we would do the same thing. Sulfur would obviously be in the middle. Fluorines would be around. And you're like, well, where do I put the other ones? Hey, you could just go here and here if you like. And we will really just do the same thing. We're going to do a single bond from the center to the outside ones. We're just going to have a few more single bonds that we normally do. So in this case, we actually did 2, 4, and 6 single bonds. So that is 12 electrons. The rest are going to go on the outside. So that's 12. That'll be 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. I hope I got you there after that. 42, 44, 46, and 48. I got them all. And at that point, we're out of electrons. And clearly, in this case, you can see the sulfur has actually 12 electrons around it. Again, it's able to do that because it has those d orbitals available to it. Any questions on that there? So why don't you draw a couple of these here? Let's do, why don't you draw, let's do BRF5. Let's do CLF3. And let's do XE F4. All right, draw the Lewis structures for. Yeah, let's take a look, see how you're doing. So again, we'll approach this the same way. We got 7 for our bromine. We got 5 times 7 for our fluorine. That's like a 35 and 7, so 42 valence electrons. Between bromine and fluorine, obviously bromine is lower down on the group there, so it should be in the center. Obviously, there's also 1 of them and 5 of the other. So fluorine should never be in the middle. So we'll do our fluorines around. And again, you can put that 5th one wherever you want. We'll do a single bond to each of them. And that's 2, 4, 6, 8, 10 electrons. So we still have more to put on. So we have 10 electrons. That would be 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40 at that point. So I now have 40 electrons. I still have 2 more to go. Just like the other way, we then go to the center atom and we would put them on as a pair of dots on the central atom. That now has 42 electrons. Everybody has 8. And in this case, bromine has more than 8, which is okay. Again, it is below sulfur there on the periodic table. So it's able to do that. Any questions on that one there? Same thing, looking over here at the ClF3. So that's 7 plus 3 times 7. So that's like a 21, 28 valence electrons. Once again, here, chlorine in the middle, fluorine on the outside. Going to do a single bond to each of them. That's going to be 6 electrons. Then that would be 8, 10, 12, 14, 16, 18, 20, 22, and 24 electrons at this point. I actually have 4 more electrons to go. Again, they go to the center in pairs of electrons. So that would be our 26, and that should be our 27, or 28 in that case, if I know how to count. That is 8 for everybody on the outside. Again, here, chlorine, no problem going over. It is right next to sulfur on the periodic table, which means it also has the d orbitals to allow it to do so. Any question on those first 2? Lastly, here we got our friend xenon, which is group 8, actually, which is very common. You see a lot of noble gases kind of pop into some of these expanded octets. Plus 4 times 7. It's like a 28, and 8 is, like 36, I think. I hope. I was going to pull out the calculator, but I held off. All right, so that's xenon, that's fluorine, 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 and fluorine. So single bond in and up here, going to give us 2, 4, 6, 8. Who do we appreciate? That is 10, 12. Thank you. I'm here 4 days a week. That is 8, 10, 12, 14. 16, 18, 20, 22, 24, 26, 28, 30, 32. Still have 4 more to go. Again on the center, 34 and 36 in this case. Any questions on drawing the expanded octet there? So you really, as you can see, you really can follow the same sort of steps that we did with obeying octet rules. And you can apply it to this as well. All right, before we finish up this here, a couple of things on this. Obviously, if it says to obey the octet rule, yes. And if it doesn't say anything, then obviously you could draw it either way. Now, to tie this together with what we were talking about with formal charge. So for example, if we do look at SO4, say 2-, which is sulfate, that is 6 plus 4 times 6 plus 2, 32 valence electrons. And if we follow our sort of approach there, you will end up with a structure that looks something like this. Now, maybe you Googled it to get the answer. And if you did this in your previous class, your teacher knew you did that, by the way, and you'd come up with this structure. That's why you shouldn't Google things if you're not sure, right? You should do it yourself. Right. So if you laid up that structure in the previous class, they're gonna go like, we don't really did expanded octets in that class. Yeah, I'm not really sure why you're laying up that structure. All right, but if you did this is another possible structure, and we could actually look at each of these and use our formal charts to decide, really in this case, is the single bonded approach really always the best approach? So if we look at the oxygen here, which they are all the same, that would be 6 minus 6 for our non-bonding electrons, minus 1/2 of 2 for our bonding electrons. And that is going to give us a -1. So each of these oxygens that are single bonded will carry a -1 formal charge in this particular case. If we look at our single bonded sulfur in this case, that is 6 for the sulfur minus 0, as there's no dots, minus 1/2 of 8 for each of the lines, or the total of all the lines together. And that gives us a 6 minus 4, a +2 formal charge on this guy. Now, if we double bond up a couple of the oxygens in this case, let's see how that helps. So our single bonded oxygen will come out the same. 6 minus 6 minus 1/2 of 2, going to give us -1. So we do have a -1 here, -1 here. Our double bonded oxygen will be 6 minus 4 for the non-bonding electrons, minus 1/2 of 2, 4 for our double bond. You go 6 minus 4, which is 2, minus 2, which is 0. So the formal charge on these guys are going to be 0. And if we looked at our double bonded sulfur and our single bonds on the sides, we end up with 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12. That is 6 minus 6, which is 0. In this case, based on formal charge, which one is the better structure? It is the one on the right. We really minimize the formal charge to 0 on most things. We also have our negative formal charges on the oxygen, which is more electronegative. We also have really minimized more so here the formal charge on the sulfur, right? It went from 2 to 0, right? So that's 2 and 3s are really larger sort of formal charges. So by making those double bonds, in this case, if you were asked to draw the best Lewis structure based on formal charge, it should be this guy on the right where you make those double bonds. And we could do that now that we know officially we could do that because, again, sulfur has the ability to do that. Not necessarily you need to do it in every situation, but in this situation, it actually does benefit in terms of formal charge and makes a better structure. Question on that there. All right, that wraps up chapter 3 here. So we're going to continue on to chapter 4, which is really a continuation. So now we talked about drawing all this stuff. We're going to talk about everybody's favorite stuff, geometry, molecular polarity. Okay, so this is really chapter 4, which is really sort of a continuation of what we've been talking about, which is basically still bonding. In this chapter, as I mentioned, we're going to talk about geometry. We will also talk about hybridization, and we'll talk about molecular polarity, more than just diatomic molecules, but obviously when you have multiple atoms that are present. So let's talk a little bit about molecular geometry first. So molecular geometry does sort of refer to the 3 dimensions of the atoms in a particular molecule. We can use really our Lewis structures, and more so not necessarily just the structure themselves, but really how many bonding electrons, non-bonding electrons are present to help us determine what the geometry of that particular molecule is. Whenever you're doing geometry, it is always about the central atom. So the central atom is always the most important one that you want to look at, and it is the one that helps you determine what geometry that you're looking at. We are going to talk about 2 different types of geometry sort of names. One is sometimes referred to as the electron pair geometry name. And the other one is the molecular geometry. R is sometimes just referred to sometimes simply as the shape of the molecule. So as we'll talk about, the electron pair geometry describes how the electrons are arranged around the central atom in three-dimensional space. The molecular geometry or the molecular shape basically describes overall, taking into account all the electrons that are present, the types of bonds that there are. It takes into account how the overall molecule will move. The bonded atoms will move as a result of maybe non-bonding electrons being there or not being there. They'll have a little bit more room to sort of move, and the overall molecule itself will take on a more different geometry that occurs. What we will see is in certain situations, both of these names will be the same. And in other situations, the only name that will actually change will be the molecular geometry name. The electron pair geometry will remain the same, regardless of sort of what's going on, but the molecular geometry shape or the shape of the molecule will change based on it. And it's really based on the idea of electrons. And obviously electrons within a bond, they're all negatively charged, which means, frankly, they do not want to be near each other, right? Because they have the same charge. But they're kind of forced to be there as they get kind of locked into place. So what ends up happening, as we'll see as we go through the different geometries, is in certain situations, especially when we have non-bonding electrons or lone pairs present, because we have non-bonding electrons, that means that we are missing perhaps a bond to an atom, right? There's kind of empty space-ish, if you will, where those non-bonding electrons are, not an actual another atom sitting there. It allows those molecules and those electrons to sort of get away from each other. Really, the electrons get away from each other a little bit more than they can when they're kind of locked into place with an atom in each of the spots. They can have a little less flexibility that occurs. And that's really why we do see the differences in the molecular geometry or the shape name rather than electron pair geometry, because of that extra space is sort of created when we sort of lose a bonded atom. Obviously, as we've been talking about, bonding obviously only involves those valence electrons, and that's VSEPR here, which is valence shell electron pair repulsion model, hence the abbreviation. That is a mouthful. And really, when we look at these sort of molecules, they are divided really into a couple of different categories. And again, the main thing is always should focus on the central atom. Now, again, if you have multiple central atoms, you want to look at each of them kind of separately from each other. But you do want to look at the central atom, and it's whether or not they have lone pairs. So there are certain molecules that do not have lone pairs. That pretty much means when you draw your Lewis structure, no dots, right? And there are molecules that do have lone pairs on the central atom. That pretty much means when you draw your Lewis structure, you got dots on the central atom. So that's a quick way to do it. Probably the most important rule when doing geometry and doing any type of geometry is really the first one there. When we have a double bond or a triple bond that you draw in a Lewis structure, it counts as only one electron pair and it counts as only one bond. So effectively that double bond or triple bond is working as one electron unit, if you will. And that is really the most important thing. So if you have a double bond or a triple bond, you count it as one electron pair and one bond. And that's really important because, frankly, most people, myself included, cannot really visualize things in their head like three-dimensionally, like what it looks like. Yes, so it really does come down to geometry most of the time. For most people, it's like a memorization and of the names. And basically the two things that's really important when you're doing that is how many electron pairs there are around the central atom and how many bonds. And if you know that from your Lewis structure and you know the chart, that's really the best way for most people to do it. Again, visually is like, all right, this guy's moving this way or that way. Most people, can't visually do it. The other thing that comes up is, as we talked about, you could draw resonance structures. So you could really apply this geometry to any resonance structure. And frankly, in most cases, you will get the same geometry regardless of which resonance structure you're looking at, because they're really all based off of the same thing. All right, so let's take a look at geometry, and let's really start with the simplest thing that you could have, which is frankly a diatomic molecule. So a diatomic molecule really does not have a central atom because frankly there's only two, right? There's just two things bonded to each other. And the old saying, right, short distance between 2 points is a straight line, right? And that's basically the deal here. So whenever you have anything that is diatomic, the geometry really is always going to be linear because they're basically just arranged in a straight line from each other. That doesn't matter if it is two different things. It doesn't matter if it is two similar things. It doesn't matter if it's a double bond or a triple bond. In terms of the geometry, all of these guys here would be linear. Again, double bond, single bond, triple bond, same elements, different elements. It doesn't matter. If you have two things, the only way that they can be arranged basically is through that straight line. And again, it will always be linear. Now, when you get to molecules that have 3 or more atoms, you do need to want to look at the central atom. And as I mentioned before, really, we'll see a table towards the end. And sometimes you make a table. I think there might be a table up on Canvas or not, but a good way to do it is, again, the number of electron pairs and the number of bonds that you have going on. So let's take a look at the first example here, something like beryllium chloride. And when we look at something like beryllium chloride, again, the two things that I'm going to look at is the number of electron pairs and the number of bonds. And again, it is always the central atom that you want to look at when you do that. So clearly our central atom here is beryllium. It's an incomplete octet. And frankly, we got 1 electron pair here, 2 electron pairs there. And we also have 1 bond and 2 bonds there. Now, starting with our first name, which is our electron pair geometry name. Something with 2 electron pairs is a geometry known as linear. Something with 2 electron pairs and 2 bonds that are happening, its molecular geometry or shape is also going to be linear. It is basically a bond angle of 180 degrees apart from each other. So that makes a bond angle of 180 degrees. The bond angle always goes with really the electron pair geometry in most cases. And again, the electron pair geometry goes with really the number of electron pairs around the central atom. When you are counting electron pairs around the central atom, as we mentioned before, double bonds, triple bonds count as 1 electron pair and 1 bond. And we are looking for total number of electron pairs. Doesn't matter if they're dots, doesn't matter if they're lines. The total number of electron pairs is what we're looking around the central atom. So in this case, electron pair geometry is linear. Overall shape is also linear. The frankly deal here is you have 2 electron pairs. They get as far away from each other as possible. And that's a straight line, right? They all end up on opposite sides basically of a straight line. And that gets you basically that overall shape of linear that's going to occur. Obviously, these are all bonds. So as those electrons moves, the atoms move with it. That gives it that overall shape. The next example is something with a central atom and 3 things attached, like BF3. And in this case, the number of electron pairs, we have 1 electron pair, 2 electron pairs, and 3 electron pairs. The number of bonds here, also 1, 2, and 3. So something with 3 electron pairs, the electron pair geometry name is going to be trigonal planar, or some people call it triangular. With 3 electron pairs and 3 bonds, the best that they could do now, since we have an extra atom involved here, is these guys kind of go this way, the top guy goes that way, these guys go that way, these guys go this way, and we end up with a molecular geometry or shape of also known as trigonal planar. And it has a bond angle of 120 degrees. It is basically making a triangle. Yes. So in this case, with the addition of that third sort of bonded atom there, again, as those atoms move, they can only get so far away from each other before they get too close for comfort. So they kind of back out, and we end up with this more trigonal planar geometry of 120 degrees. Again, both names here the same. Yeah. The next sort of geometry that we come across, and you might be familiar with as well, is a central atom that has 4 things attached. And a central atom that has 4 things attached is something like methane here. And methane, in terms of the number of electron pairs, we have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. And in terms of bonds, we also have 1, 2, 3, and 4 bonds. Something with 4 electron pairs, the electron pair geometry is tetrahedral, is what most books use nowadays. If you're old like me, tetrahedron, sometimes people will use. Something with 4 electron pairs and 4 bonds. So from the last one, we had 3 bonds. Now we're adding 4 bonds. Again, that's going to allow these guys to only move a little bit away from each other. And we're going to also end up here with a molecular geometry of tetrahedral as well. And that has a bond angle of 109.5, kind of like a triangle on the face and a little pyramidal type of shape sort of happening there on the bottom as they sort of spread out from each other. Once again here, both names going to be the same. And as you can see, the bond angle sort of shortens up, right, because of the extra atoms that are added, meaning those electrons don't have as much flexibility to move away from each other as they did in sort of the linear situation where they can completely get to opposite sides of one another. So these geometries here you're probably familiar with, but of course our good friends, the expanded octets, also have some geometry that goes with it. So let's talk about that guy next, I think. And this is an example of something with 5 guys attached here. And that's PF5. Number of electron pairs, again, around the central atom, we have 1 electron pair, 2, 3, 4, and 5 electron pairs. Also has 5 bonds happening here. And this obviously is an expanded octet. And again, phosphorus, which is right next door to sulfur, has the ability to do that, as we talked about earlier, with the d orbitals available to them. Something with 5 electron pairs is known as electron pair geometry, as triangular bipyramidal. Something with 5 electron pairs and 5 bonds. Now we're adding even one more sort of atom in there that's going to allow less space for everybody to kind of spread out from each other. We're going to end up with a molecular geometry here, or a shape, also known as triangular bipyramidal. It actually has 2 bond angles. It has a 120 degrees and also a 90 degree, as you can kind of see the right angle there, if you will. And here, maybe you can see it, it actually makes like that trigonal planar triangle happening through those guys there, just like we see with just straight trigonal planar. So it has the 120 and 90 degree bond angle. Those guys where I just drew the triangle there up on top, those are sometimes referred to as equatorial positioning, because it's like the equator right there in the center is where they're sitting. Axial would be above and below sort of the plane there, or the center of the molecule, or those other sort of situations where they're at. The next geometry is also going to be an exception to the octet rule, and that is going to be our SF6 that we drew earlier. Our SF6 here, number of electron pairs has 1, 2, 3, 4, 5, and 6. Number of bonds also going to be 6. 1, 2, 3, 4, 5, and 6. Something with 6 electron pairs has an electron pair geometry of octahedral. And something with 6 electron pairs and also 6 bonds will have a molecular geometry of octahedral as well. Has really just 90-degree bond angle, maybe easier to see on this picture, sort of 90 degrees sort of happening at each of those sort of points. In this case as well, our molecular geometry and electron pair geometry names are the same. Really, as I mentioned before, sort of the best way to do it is through memorization, and number of electron pairs, number of bonds, really the kind of the easiest way to do it. Any questions on that so far? Up until this point, both of these names have been exactly the same, the electron pair geometry name and the molecular geometry name. And the reason for that is when we look at the central atom of each of these guys that we just drew or looked at, there are no non-bonding electrons, right? There are no dots, basically. So all these guys, when you have no non-bonding electrons around the central atom, will end up with this same name, the electron pair and the molecular geometry. And that is because they're all bonding electrons, which means on the other end of those electrons is an atom. So as those electrons move away from each other, so does the atom. And that means that the overall shape ends up being the same shape as how the electrons basically got away from each other because of that. So whenever you have any Lewis structure where no dots on the central atom, no non-bonding electrons, both of those names should be the same. It is when we start adding non-bonding electrons to the central atom that we do get some differences in the name. And the name that changes is the molecular geometry name. The number of electron pairs there will still be the same, but because we are actually lacking the atom there, it allows those electrons to move a little bit more and those bonded atoms to move a little bit more and get away from each other a little bit more because they're not stuck with that extra atom there. And it gives us a different overall geometry shape of that molecule. So let's talk a little bit about that. When we do get non-bonding electrons involved, there's really 3 types of electron forces that come in contact with each other. The best situation is what we just talked about, which is bonding and bonding electrons near each other, kind of lines and lines on your Lewis structure. So when you have lines and lines near each other, that's pretty tolerable. The next kind of tolerable and gets a little bit worse is when you have lone pairs near bonding electrons. So that's like dots and lines near each other. They kind of don't like to be near each other. The worst situation in terms of repulsion is you got free electrons, non-bonding electrons near each other, dots near dots. That is like the worst situation. And it's also the best situation in a sense because that means you don't have as many atoms there. So it gives those electrons a lot more room to move around and spread out from one another. And again, it is this presence of those non-bonding electrons there gives more room and allows the overall shape to really change because of the lack of those extra atoms being present. So let's take a look at an example of that. So the first example would be something like sulfur dioxide. And if you draw sulfur dioxide, it will look like this. And once again, we want to look at the central atom. And let me draw it a little bit bigger here. I'm not going to put the electrons on the outside here. So looking at the central atom here, the number of electron pairs that this central atom has, how many electron pairs does the central atom have? It has 1 electron pair here, 2 electron pairs there. Double bond counts as just 1. So it actually has 3 electron pairs. Number of bonds in this case, there are 2 bonds. Double bond counts as 1, single bond counts as 1. So that is 2 bonds. So 3 electron pairs and 2 bonds. Now, the electron pair geometry is not going to change because there's still 3 electron pairs. So something with 3 electron pairs, electron pair geometry is trigonal planar. But now, because we don't have that third bond like we have in a trigonal planar molecular geometry, we have that empty spot, if you will. Not really empty, but it's where there's non-bonding electrons. It's going to allow the bonded electrons to kind of move away. So they're going to kind of go this way. This guy is going to kind of go up. And we will get a molecular geometry. I go with angular. Some people use bent. Some people use bent angular for this one. But personally, I'm going to go with angular, and we'll talk about why that is in just a second. But some people will do bent angular. But I'm going to go with just angular, and we will as well here. The bond angle here is actually less than 120 degrees, and it's a little less than 120 degrees because of that missing atom that's bonded there. So it gives it a little bit more room to move. So 3 electron pairs, but only 2 bonds will give us this angular sort of shape, not as sharp as a bent or V shape that we'll see a little bit later on. The next sort of example here is something with 4 electron pairs, but only 3 bonds. And this is something like NH3. Number of electron pairs. We have 1, 2, and 3, and one more makes 4. Number of bonds in this case is only 3. 1, 2, and 3. So once again, the 4 electron pairs here means that the electron pair geometry will still be tetrahedral. But again, because we're missing that 4th bond and we have those non-bonding electrons, it's going to allow this molecule to basically move a little bit more. And we're going to end up with a molecular geometry known as trigonal pyramid. Kind of makes like a triangle and then a pyramidal type shape at the bottom there. Bond angle here going to be less than 120. As you can see there, it's about 107.3 in this particular example, which obviously is less than, I'm sorry, not 120, it's less than 109.3, 109.5. It's tetrahedral, so it's less than 109.5, which obviously 107.3 is a little bit less than that because of the non-bonding electrons that are present. Question on that one there. Take a moment here to talk about a couple of names. This is trigonal pyramid. 3 electron pairs, 3 bonds is trigonal planar. Yes, there is a difference between those two. Yes, so on your exam or something, don't just write trigonal because you will get one of those. Yes, and don't write like trigonal planar, I mean pyramid, one of those. Yeah, so make the decision. Don't let me choose. I failed chemistry, so you know I'm going to choose wrong for you. So make sure you do not just write trigonal for those. Make sure you specify which one you are talking about. Next example that you might be familiar with is our friend water here. Water, if we look at the central atom, number of electron pairs, we got 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Number of bonds, going to be 1 bond, 2 bonds. So once again, our electron pair geometry name is based off of the number of electron pairs there. So it is 4, does not change. So electron pair geometry will be tetrahedral. But now we actually have all 3 sort of interactions happening here. We have bonding electrons near bonding electrons. We have non-bonding electrons near bonding electrons. And we got non-bonding near non-bonding electrons, which is the worst case. So basically what happens is these non-bonding electrons decide, hey, we're going to go like this way and this way away from each other. That's going to bring those bonded guys kind of down as well. And we will end up with a molecular geometry or shape of bent or V-shaped. So we're going to save in this class bent or V-shaped, really bent for this geometry here. And the reason for that is the bond angle here is less than 109.5, 104.5, as you can see there. When we looked at the angular one for SO2, the bond angle was less than 120. So there's a kind of a big difference in terms of the bond angle between those. So again, for the 3 electron pairs and 2 bonds, we're going to go with angular. 4 electron pairs, 2 bonds, we're going to go with bent for that one here. Any questions on that? All right, so now we have a few more geometries to talk about here, and these are going to be our expanded octets that we saw earlier, our trigonal bipyramidal, and our octahedral. So let's take a look at those. Next example we could have is something that looks like this. And if we look at our central atom number of electron pairs, we have 1, 2, 3, 4, and 5 electron pairs. And in terms of bonds, number of bonds here going to be 2. 1 and 2. Once again, electron pair geometry name is based off of the 5, which is what we saw before. That is triangular bipyramidal. With those non-bonding electrons there and the 2 bonded electrons, allows those bonded guys actually to get to opposite sides of each other. And the molecular geometry here is actually going to be linear. And that allows basically these bonded guys to get 180 degrees away from each other. And these guys in the middle sort of make like a triangle. But the bond angle here is 180 degrees, basically. It allows those guys basically to get that far away from each other. The next geometry, which is also an expanded octet, is where we have basically 5 electron pairs and 3 bonds. So something like ClF3, looks something like that. And when we look at the number of electron pairs, we have 1, 2, 3, 4, and 5. Number of bonds in this case, we have 3. Which is 1, 2, and 3. Once again, electron pair geometry name going to be based off of that guy there. So that is 5. So our electron pair geometry going to still be triangular bipyramidal. Now we do have that third sort of atom we didn't have in the other case. So that's going to keep those atoms not being able to get as far apart from each other. And it's actually going to end up with a molecular geometry, as you maybe see from the picture, or the shape of it as T-shaped. And kind of makes a T. Yeah, so kind of makes that T right there. And you got a bond angle there of 90 degrees, a little less than 90 degrees, but you got about a bond angle of about 90 degrees. 90 degrees, as you can see there. Questions on that one? All right, so I have a few more to go, so we're going to finish up the last few here. The next one that we have is still 5 electron pairs, but we got a extra bond in there, so we're going to have 4 bonds in this case. So number of electron pairs, 1, 2, 3, 4, and 5. Number of bonds, only 4 in this case. 1, 2, 3, and 4 bonds. Once again, our electron pair geometry name going to be based off of the 5 that we see here. And that is going to be still our triangular bipyramidal. With that 4th atom added from the previous one, again, not going to allow everybody to kind of get away from each other as possible. The molecular geometry, our shape of it is actually going to be what is referred to as seesaw. Some people call this a distorted tetrahedral. If you're old like me, sometimes that pops up. So sometimes people will call that a distorted tetrahedral. I think your book and most books call it now seesaw. Kind of looks like a seesaw, which is why they kind of go with that. It's basically a seesaw there. And the seesaw actually has the bond angle is a little less than, like we see there, 120 and a little less than 90 degrees in terms of their bond angles that happens. Any questions on that one there? Now, in addition, obviously, we can see our triangular bipyramidal expanded octet. Our octahedrals also have some expanded octets, obviously, with some non-bonding electrons involved. So let's take a look at those to finish it out. The next one is XEF4, which I think we drew a second ago. If we look at the number of electron pairs, we got 1, 2, 3, 4, 5, and 6. Number of bonds here going to be 4. 1, 2, 3, and 4. Once again, the electron pair geometry is based off of the 6 electron pairs, or electron pair geometry going to be octahedral. With 4 bonds there, they do spread out into basically a square that's within a plane, and the molecular geometry here is going to be square planar. Has a bond angle of 90 degrees here, as it basically makes a square within the plane. Those 2 non-bonding electrons go in the opposite direction. It's a better square drawn that way, I guess. And the last geometry that you'll be responsible for is the octahedral geometry, bless you, where we have 6 electron pairs and 5 things attached. So number of electron pairs going to be 6. 1, 2, 3, 4, 5, and 6. Number of bonds here will be 5 in this case. 1, 2, 3, 4, and 5. And once again, those 6 electron pairs going to give us an electron pair geometry, also of octahedral. Again, the presence of those non-bonding electrons, and really only the 5 guys that are bonded there, will give us a molecular geometry, our shape of square pyramid or pyramidal. And again, kind of makes a square and this sort of pyramidal type of shape that's sort of happening. Bond angle also 90 degrees sort of happening here as well. So these are the electron pair geometries, which again describe the electron pair how the electrons are arranged around the central atom. As you can see here, when we start introducing non-bonding electrons to the central atom, those repulsive forces come into play, and they have a little bit more room to move around because of the lack of the actual bonded atom being there. And we do see the difference in the molecular geometry name or the shape of it. Here's a table similar to what you have in your book that goes through all those ones that we just talked about, and